Imagine entering a virtual classroom where you are not simply watching a lecture, but seated around a table, embodied through an avatar, interacting within a spatial environment. Virtual education promises immersion, but which design elements actually shape the learning experience? In this study, we go beyond testing a single feature. We introduce the VCIMA framework to systematically compare avatar type, classroom perspective, and viewing device within one controlled experimental structure. By integrating these dimensions into a unified evaluation, we aim to provide empirically grounded design guidelines that can support the next generation of virtual classroom systems. With the advancement of multimedia and computer graphics technologies, 3D avatars are increasingly used in immersive educational systems. However, many previous studies examine individual design dimensions in isolation, such as avatar realism, device type, or layout configuration. In contrast, our study does not propose a new pedagogical theory. Instead, we provide a controlled comparative evaluation of how these dimensions function together within one unified experimental structure. In virtual classrooms, avatars act as mediators between learners and instructional content. From a human-computer interaction perspective, embodiment may influence social presence and engagement. This study evaluates how different forms of avatar embodiment and spatial arrangement affect measurable learning and experiential outcomes. We conducted a controlled experimental study with 150 university students using a mixed factorial design. Viewing device was treated as a between-subject factor, comparing immersive VR and traditional 2D screen conditions. Avatar type and layout perspective were treated as within-subject factors, allowing participants to experience different avatar embodiments and spatial configurations within the same experimental structure. The instructional content was a standardized 10-minute calculus lesson, focusing on derivative-based limit evaluation, using L'Hopital's rule. The lesson was kept consistent across all conditions to ensure comparability. All virtual environments were developed using Unreal Engine, and VR conditions were implemented using Pico 4 Pro headsets. Scene presentation order was counterbalanced to reduce potential order effects. After each instructional session, participants completed validated measurement instruments, including the Simulator Sickness Questionnaire to assess physical discomfort, the E-Group Presence Questionnaire to measure sense of presence, and the Film Immersive Experience Questionnaire to evaluate immersive dissociation. Learning performance was assessed through a knowledge test consisting of 10 multiple-choice items and 2 procedural computational problems. All questionnaire items were rated on a 7-point Likert scale, and the entire experimental procedure lasted approximately 40 minutes. The roundtable configuration was designed to simulate collaborative face-to-face interaction within a virtual environment, where students are spatially positioned around a shared focal point. Unlike linear classroom arrangements, this circular layout allows participants to maintain peripheral awareness of peers and instructors simultaneously. According to our results, this configuration consistently produced the highest presence and immersion scores across VR conditions. This suggests that circular spatial arrangements may strengthen embodied perception and peer awareness, supporting a stronger sense of being there in immersive learning contexts. The row column layout replicates the spatial logic of a traditional lecture hall, emphasizing structured alignment and centralized instructor visibility. While this format reflects familiar educational environments, our results show that in VR conditions, it produced lower presence and immersion scores compared to the roundtable configuration. This indicates that simply transferring physical classroom structures into virtual space does not necessarily optimize immersive engagement. In virtual environments, spatial interaction and perceptual dynamics may function differently from physical classrooms. The fixed perspective provides a stable and content-centered viewing mode, reducing spatial movement and maintaining visual focus on instructional material. This configuration may be beneficial during detail-oriented explanations or cognitively demanding tasks, where minimizing environmental complexity supports clarity. However, reduced spatial interactivity in this layout was associated with lower immersive dissociation compared to more dynamic configurations. This suggests that while stability may enhance focus, it may simultaneously limit embodied immersion within virtual learning environments. The 3D interactive avatar condition demonstrated significantly enhanced presence and immersion. According to our ANOVA results, avatar dimensionality had a significant main effect on IPQ scores, with 3D avatars outperforming 2D avatars across layouts. The effect was most pronounced in the roundtable configuration. Similarly, for immersion measured by Film IEQ, 3D avatars significantly increased environmental dissociation under VR conditions. However, this advantage did not emerge under 2D screen conditions, indicating that 3D avatars rely on stereoscopic depth cues and spatial interactivity. The combination of VR, roundtable layout, and 3D avatars yielded the highest presence and immersion scores in the study. These findings suggest that depth representation and natural embodied interaction are essential for achieving a strong sense of presence in immersive virtual classrooms. In this condition, we used 2D non-interactive avatars as a baseline control. As described in our paper, 2D avatars follow a unidirectional instructional approach, meaning that students cannot engage in real-time adaptive interaction. The avatar does not respond dynamically to learner input, which limits multimodal feedback and reduces interactivity. Quantitative results show that 2D avatars consistently produce lower presence scores in IPQ and lower immersion scores in Film IEQ, especially under fixed layout conditions. The lack of stereoscopic depth and embodied spatial cues restricts environmental dissociation and social realism. Although 2D avatars remain practical due to low technical requirements and accessibility, they provide a significantly less immersive experience compared to 3D interactive avatars. Therefore, in our framework, 2D avatars serve primarily as an experimental control to evaluate the added value of dimensionality and interaction. Presence was significantly influenced by viewing medium. Participants in immersive VR conditions consistently reported a stronger sense of being there compared to those in 2D screen environments. Beyond device type, spatial layout also played a substantial role. Among the three configurations, the roundtable arrangement produced the highest presence levels, suggesting that circular spatial positioning may enhance peer awareness and spatial co-presence. In addition, avatar dimensionality contributed to presence perception, with three-dimensional avatars generating higher presence ratings than two-dimensional avatars. Taken together, these results indicate that presence in virtual classrooms is shaped by the interaction between embodiment, spatial configuration, and display medium rather than by any single factor in isolation. Immersion, operationalized through dissociation scores measured by the Film IEQ scale, showed a similar but slightly more nuanced pattern. Immersive VR conditions produce substantially stronger dissociation from the physical environment compared to 2D display settings. Spatial configuration again played an important role, with the roundtable layout demonstrating the strongest immersive effect, followed by the fixed configuration, while the row column arrangement showed comparatively weaker dissociation. Notably, the immersive advantage of three-dimensional avatars emerged primarily under VR conditions. In 2D screen settings, avatar dimensionality did not produce a significant difference in immersion. This suggests that the benefits of 3D embodiment depend on stereoscopic depth cues and spatial interactivity provided by immersive VR hardware. Simulator sickness scores were significantly higher in VR compared to 2D viewing conditions. Layout configuration significantly influenced SSQ levels, with the roundtable condition showing lower sickness scores than the row column condition. However, no significant interaction effects were observed between viewing perspective and presentation mode. It is also important to note that all SSQ mean scores remained within mild discomfort ranges. Learning performance was measured using a 100-point knowledge assessment. VR conditions showed higher overall performance compared to 2D conditions. The roundtable VR with 3D avatars produced the highest total score. Three-dimensional avatars demonstrated a statistically significant advantage over two-dimensional avatars. Based on the integrated findings, several design implications can be drawn. First, viewpoint flexibility appears important, as the roundtable configuration enhances spatial immersion and peer awareness, while fixed perspectives can support detail-oriented instructional moments by stabilizing visual focus. Second, interactive 3D avatars contribute to presence and immersion, particularly when combined with spatially dynamic layouts, suggesting that embodiment and layout should be designed in coordination rather than independently. Third, emotional realism and adaptive avatar behavior remain critical, as low interactivity may reduce engagement and weaken empathetic connection. Overall, these findings suggest that effective virtual classroom design should balance spatial interaction, instructional clarity, and adaptive avatar responsiveness, rather than relying on a single configuration. In conclusion, this study provides an integrated comparative evaluation of avatar type, layout perspective, and viewing device under the VCI-MA framework. While several findings align with prior research in VR-based learning, the primary contribution of this work lies in structuring these design dimensions within a single controlled experimental evaluation, offering a systematic basis for comparison rather than claiming entirely novel learning effects. Looking forward, future research will extend this framework through longitudinal learning assessments, broader factorial condition coverage, and AI-driven adaptive avatar behaviors, with the aim of further validating and refining immersive virtual classroom design.